Hi, this video is a presentation for Physics 2211, Lab 1 on constant velocity. In this video, I will introduce the experiment and explain some key terms and formulas helpful to understanding the physics behind the experiment, show my analysis of the physically observed motion, produce a complementing computational model, compare the results between the two processes, and conclude by discussing the ramifications of this experiment. The first key concept to understand is what this experiment was testing: constant velocity. We know that velocity is a vector, and therefore contains two important components, magnitude and direction. So if a velocity is constant, the rate at which an object travels, its acceleration, remains the same. Additionally, the direction the object travels in remains the same as well. The second key concept to understand is Newton's second law of motion. This law tells us that the net force of an object is equal to its mass times its acceleration. The momentum principle, which states that the change in momentum is equal to the net force times the change in time, is also very useful. And since in this experiment we are testing conditions where the velocity is constant, the net force should equal 0 because the acceleration at constant velocity is 0, indicating that no net force is acting on the system. Additionally, a few key formulas to be familiar with are the velocity update and the position update formulas. These two formulas, along with the formula for average velocity, help us determine the final velocity or position of an object at any given moment, which in this experiment is critical to determine whether or not the object truly has a constant velocity or not. To test for constant velocity in this experiment, I recorded a video of a water bottle rolling across a flat surface. While the entire video includes the beginning and the end of the motion, I trimmed the video to only include the middle portion to capture the most accurate velocity data. This video was then uploaded to a software called Tracker, which enabled me to further analyze the events of the video. I changed the axis point to align with the movement of the water bottle so that it traveled solely along the x-axis, and tracked a specific point of mass on the water bottle, aiming for that point to be as close to the center as possible in each frame of the video, beginning at frame 24 and ending at frame 85. The program took each of those data points and generated a position versus time graph, which can be seen on the right side of the screen. With observational data now recorded and analyzed, I moved to the second portion of the experiment, which was to create a computational model based on my experiment. Using GlowScript and available code as a template, I was able to generate expected results for the conditions of my observational data. These real-life conditions needed to be reflected in the code, and therefore some aspects needed to be changed. First, under the initial conditions section, the velocity data needed to reflect the velocity of the bottle for my video. So choosing two sets of data points from the analyzed tracker data, I could calculate the average velocity using the formula change in position divided by change in time. This resulted in a velocity of 0.280303, which was inputted into the GlowScript code in the x component as the motion of the bottle fell along the x-axis. The delta t, or change in time, also needed to be changed so that it followed the same interval of time as the data from Tracker. Two pieces of data in the calculation loop of the code also needed to change. First, the parameter, while t is less than 2, needed to be the same value as the final time point from the Tracker data, which was 2.031 seconds. Additionally, the update object's position line also needed to be altered to reflect the observational data, and so by multiplying the velocity by the change in time, the x component of the position update could be calculated, which was 0.00925. Once the code accurately reflected the conditions of the experiment, it could be run to generate a model of the motion of the object shown on the screen. It also generated expected position and time data for the experiment. Now, having successfully obtained two sets of data for the experiment, a comparison can be made, and as you can see from the graph on the screen, the two sets of data are incredibly similar. This means that the observed data is pretty accurate to what computationally you could expect in these conditions. Another important thing to note about the graph is that each data set generated a straight increasing constant line, indicating that the experiment was successful at observing and analyzing an object experiencing motion at a constant velocity. Reflecting on the experiment, one major what-if question that comes to mind is what would have happened if we observed and analyzed an object traveling only along the y-axis instead of the x-axis. This would change our experiment completely, because an object under these circumstances would in fact be experiencing a net force, a change in momentum, acceleration, which would in turn mean that the velocity would not remain constant due to the effects of gravity. Under ideal real-life conditions, the observed and expected data from this experiment would have been identical. However, we know that frictional forces, along with other potential forces, are present when the water bottle rolls across the wooden shelf. These forces will prove to be critical as we advance in our studies of physics, But for now, we can conclude that this experiment is a fantastic way to learn more about the effects of velocity in relation to Newton's second law of motion, a key concept for this class. And understanding the underlying physics of this experiment helps us understand even more about the world around us. Thank you.